Hi, in this video, this is actually the first video that I want to talk about factorizing the polynomials, okay? I will not be able to finish all what I want to cover in one lecture. I need to continue to see how it goes, okay? So today we start with this factorization. After this is finished, as usual, I will upload a PDF file containing some problem sets related to the material that I will cover here. And as usual, I will upload the solution of those problems in a separate video on the next week. Okay? Okay, now let us talk about factorization. What is the meaning of factorizing a polynomial? Before doing that, let me just talk about what is the meaning of factorizing a number. Let us call, for example, 12, yes? When I say that factorize 12, it means that write it as a product, not just decompose it, yes? Decompose it as a product of factors. For example, if I put right, it's 10 plus 2, of course this equality is correct, but this is not called the factorization of 2, and 12 and 10 and 2 are not called factors, they are called summands. So 12 is written as a sum here, and this 10 and 2 are called summands, yes? So this is not factorization, even though this is true, this equality is true, but not a factorization. Okay? But if I write 12 as, say, 2 times 6, then I would say that 12 is written as a product of two factors. And then in that case, I would say that 2 times 6 is a factorization of 12. Yes, in this case, these are called factors. Yes, and of course, this is a factorization. Okay, but usually when we talk about factorizing a polynomial, it means that continue factorizing until no factor can be factorized more into non-trivial factors. Because you know that, what do I mean by a trivial factor? 1 is always a factor of every number, yes? So if I add, for example, multiplied by 1 here, this is still true, and this is still in the product form, so this is a factorization. So 1, we don't consider 1 here. So, but if I want to continue the factorization more, 2 cannot be factorized more. The only way that I can write it as a product is to write 2 times 1, and for the same reason, I don't want to have 1, so this 2 is the only one. Of course, 2 is a prime number, you know that. But then 6 can be factorized one step more. So instead of 6, I can write 2 times 3, yes? So then, of course, if you want, you can combine 2 times 2 to the 2 to the power of 2, and then multiply it by 3. Yes? Okay, so this is the full factorization of 12. More or less, I want to do the same thing for polynomials. So when I say factorize a polynomial, I mean write the polynomial in a product form. Write it as a product of some factors. These factors could be numbers, or they could be other polynomials. Okay? This is one thing I want to mention. Of course, I will start with very simple examples this session, and I will increase the level of the hard questions little by little when we go to the next lectures. Okay. One more thing that I want to mention when we're dealing with factorizing polynomials is that the domain that we are working is also important. For example, of course, you all know a little bit about factorization. For example, if I write 2x plus 4, if I want to take 2 out, then what happens? It becomes 2x plus 2, yes? That's correct. This is a factorization of 2x plus 4. Why? Because 2x plus 4 is now written as a product of two expressions, a polynomial and a number. But what happens, for example, if I have this 2x plus 1? Can I still factor 2 out? The answer is actually yes. You can write equal to 2, and then you have to write x plus 1 half. What is important for this equality to be true is that when you multiply this thing back, it gives you the same expression. So let us do that. If I multiply 2 by x, it becomes 2x. If I multiply 2 by 1 half, it becomes 1. So this equality is indeed correct. And if I ask you, is this expression in the product 4? You would say yes. This is a product between the number 2 and this first degree polynomial. Okay, but usually we stop here. We do not factorize it more into this form. So what is important here is that the numbers involved after factorization in principle should be clear for you a priori. Yes, so you need to know on which domain you are working. If you want to stick to integers only, this is not a valid factorization. Yes. So you have to, if you want to work in the domain of integers, you cannot factorize this expression anymore. But if you want to work in the domain of rational numbers, then this is also valid. So in principle, before starting factorizing a polynomial, the domain of the factorization should a priori be clear to you. But usually when we don't talk about that, I don't know, in principle, we think that it should be the set of integers. And for example, I will never factorize this into this form. Okay? So, but if they tell me factorize this and the domain is the set of rational numbers, then I can factorize this in this form, of course. And I have to continue in that case because they have mentioned explicitly that the domain of factorization is the set of rational numbers. And 1 over 2 is a rational number. Yes. As another example, for example, if I have x squared and then I have minus 1. Every one of you hopefully knows from the previous lectures that this can be written as x minus 1, x plus 1. But what happens if I have this situation? Can I still factorize this polynomial? Okay, the answer depends to the domain that you are working, of course. If my domain is the set of integers or the set of rational numbers, no. The answer to this question is no, and I have to stop here. But assume that the set of real numbers is the domain that I am supposed to work in. Then, of course, I can continue. Why? Then I can write it as x squared. Instead of 2, I can write square root of 2 to the 2. And then this becomes exactly the conjugate pattern once more. So what happens, this becomes x minus square root of 2, x plus square root of 2. Yes? But this is completely valid if I am working in the set of real numbers, yes? Because the square root of 2 is a real number. But if I want to factorize this in the set of integers, in the set of natural numbers, in the set of rational numbers, I have to stop here. And I don't know if you are familiar a little bit with complex numbers, what can I do, for example, if I have this situation? Can I factorize this in the set of real numbers? The answer is no. But what about the complex domain? If I am allowed to use the complex numbers, can I proceed and factorize this? The answer is again yes. So you can write it as x squared. Instead of 1, you can write I squared to the 2. I is the imaginary unit. You know that I squared is negative 1. And then this becomes negative 1. It becomes positive 1. So then you can factorize it in this form again. So it becomes x minus I times x plus I. But if I ask you, is I a real number? The answer is no. I is a complex, pure imaginary, pure complex number. So it means that if I want to stick with the set of real numbers, I will no longer be able to factorize this expression more than that. But if I'm allowed to use complex numbers, then I can factorize it to a product of x minus I times x plus I. Yes. But of course, if you are not familiar with the notion of complex numbers, you don't really need it at all. Okay, just I wanted to mention that the domain in which we are doing the factorization is important, and whenever it is not mentioned, I take it for granted that the domain is the set of integers. Yes. If I want to work with fractions, square roots, and things like that, I have to mention them explicitly. Okay. Okay, so far so good. So let me clean this. And now here, because there is no there is no standard way of factorizing polynomials, and in principle, factorizing a polynomial could be very difficult. Okay, so this is why I want to talk a lot about the methods that someone can use to factorize the polynomials, the most famous ones. Okay, so the first method that I want to talk about, method number one, even though it is the simplest one, but probably the most important one. So what is method one? I don't know how to name it, but I can call pulling out the common factors. Or we can say factoring out, yes. Okay, and I think the best way is to start with examples. So example, so factorize so okay, number one, I have 5a squared b plus 10a to the 3 b to the 2, b to the 4, okay? So I want to factorize this polynomial, okay? The first thing is that probably you can see that this is already itself, this one itself is already in the factorized form. Yes, it's a product of 5a and b. This is also in the factorized form. Of course, if you want, you can factor 10 more to 2 times 5. But anyway, it's also in the product form. Yes, but the whole thing is not in factorized form because these are summands of the whole expression. Yes, so it's not in the factorized form yet. But let me just describe it once because I don't want you to rely on this method that I am describing right now so much. But I want you to understand what is going on. In principle, if you want to factor something out, you need to find the common factors in all the expressions involved in that polynomial. Okay, so what do I mean by this? So let me write here. So 5a squared b, if I want to write the factors, one of them is, let me write it here. One of them is 5. 5 is a prime number, so that's 5. And then the other one is a, and another one is a, because I have a times a, and another one is b. So I have these factors constituting this expression. And the other one is 10, a to the 3, b to the 4. So if I write this as factors, 10 is 2 and 5. So 10 contains a factor of 2 and 5. 2 times 5 is 10. And this I have a and a and a 3 times. And then I have b, b, and b, and b 4 times. So let us consider the common factors. So you see, 5 is a common factor. And then this a is also a common factor. This a is also a common factor. And this b is also a common factor. All the common factors can be pulled out. Yes. So what can I pull out if I want to answer this? So this is equal to, I have a factor of 5 in common. I pull it out. So let me cross it. I have a factor of a, let me pull it out, I cross it. I have another factor of a, I pull it out, I will cross it. So, and then nothing in common. Okay, I have also another factor of b. I pull it out and I will cross it. Okay, nothing is actually left here from the first one. Nothing left means 1, because in principle 5 can be written as 5 times 1, yes? And then I have a positive sign here. And then what is left from here? I have a factor of 2. I have a factor of a left. And I have 3 b's left, yes? Okay, so this is very naive way of doing that, but nobody actually do that. I hope that you can do it in your head, but nobody writes a times a. We people write a squared b, and then I have a, and then I have 2a, b times b times b is b3. So what I expect is that by immediately looking at this, you should be able to calculate this in that way. You really don't need to go through this mess. And let us check the answer is correct. How? By multiplying this back. You need to retrieve your expression. So multiply this back here, 5a squared b times 1 is 5 squared b. And then if I multiply this here, 5 times 2 is 10, a squared a is a cubed, and b times b cubed is b4, yes? Okay, so this is the way that we do for pulling expressions out. So we need to realize, we need to distinguish the common factors, common to all terms involved, and then pull them out. So let me give you one more example here. So number 2, and then let us do it quickly, yes? So then it becomes 35 x to the 3 y minus 77 x to the 2 y to the 2, and then I have minus 63 x to the 2 y to the 3. Yes, I want to factorize this. So you immediately recognize that between 35 and 77 and 63, 7 is a common factor. So I can write it as equal to, I can pull 7 out. And between x to the 3, x to the 2, and x to the 2, the highest possible x power that I can pull out is x2. Yes. And the same thing for y is just one y. So I can pull it out. I cannot extract more y's out, yes? So what is left here? In principle, if you want to see what is left, you have to divide this expression in your head or in the scratch paper by this thing that you have pulled out. So if I go to scratch paper, so 35 x to the 3 y was the original expression. I pulled that expression out, and what is left, 7 and this are simplified is 5, x2 and x cubed can be simplified to x, and y is actually gone. So what is left here is x, okay? The next one is negative. You can do the same process once more. You need to divide this by what you have pulled out, but this is easy to do it mentally. So this becomes minus 11, and then I have y, and then if I take this one, it becomes minus 9, and then I have y to the 2. To make sure that everything is in order, I really recommend you to, wait a little bit and then recheck the problem once more by multiplying this expression back. If you multiply, it becomes, oh, you see, I made a mistake here. I forgot to write 5, yes? So I multiply that there, it becomes 35 x to the 3 and y. And if you multiply this by the next one, it will give me exactly this expression. And when I multiply it back to the last one, it also gives me the correct expression. Yes? Okay. And then in some cases, what you can pull out is itself a polynomial. Okay, so I can give you this kind of examples. For example, number 3, you might have this situation: ab x squared plus y, and then I have plus 2 x squared plus y. Yes, so you see here, if I ask you what are the factors of this first term here, you would mention a is one factor, b is the second one, and the whole expression x squared plus y is the third factor. Okay, and if I ask you how many factors are involved for this expression, you would say 2 and x squared plus y. These are two factors. And then x squared plus y is in common between these two terms. So I can pull this factor out. But this factor itself is a polynomial. Yes, doesn't matter. So if I want to answer this, I pull out x squared plus y out and I open brackets. X squared plus y is pulled out. What is left is ab. In principle, you divide this by this one and you get ab. And then you have positive sign. And then you divide this by that expression, you get 2. So it's also very important to realize what's going on, because most of the time in the future, we have to do something like that. Okay, let me give you some more examples of this type. So number 4, it is 6y minus 1 to the 4, and then plus 4y minus 1 to the 3. Yes? Okay, if I ask you, is this in the factorized form? You might say no, because this is a sum. So this is a summand, and this is also a summand of the whole expression. But if you look here, this is already in factorized form. And what are the factors? The factor is 6, which is composed of 2 and 3. And this is the factor, which is composed of y minus 1 4 times. And if you hear, the factors are 2 times 2, 2 factors of 2, and then here I have 3 factors of 1 minus y minus 1, and it means that how many factors are in common? I have a factor of 2 in common between the numbers, and I have 3 common factors y minus 1. So what I pull out is a 2 and y minus 1 to the 3. Then I open brackets. So this was 2 times 3, the factor 2 is pulled out, so 3 is left. And I had y minus 1 4 times, 3 of them I pulled out, so 1 is left. So be careful, if you write it in that way, it's wrong. You have to write it in this form. And what is left here is just simply 1, 2. But if you just leave it like that, it's not completely appropriate, because nobody writes extra brackets if not needed. When you do this, you do the simplification. So simplification is also very important, even in factorization. So this becomes y minus 2. This one, I cannot do anything. By the way, you are not allowed to raise it to power 3, because the goal here is not to expand. It's actually the other way around. The final word, the final answer is given, you want to go back and see that what was the original form of that expression before expanding, more or less. Yes, so you are not allowed to raise it to power 3, because that's not this problem. You want to factorize it. But then I multiply this expression becomes 3y minus 3 and then plus 2, but minus 3 plus 2 is simply minus 1. So I would write this in this simplified form. Okay, let me go to the next example, number 5. I will have x squared plus x plus 1. Then I have minus x squared plus x plus 1. And then plus 3 x squared plus x plus 1. Let me mention once more. The problem is factorizing this expression. The problem is not expanding. If I want to expand this expression, I would multiply this x squared inside, I would multiply this negative x inside, and I will multiply this 3 inside, and then I will look at the similar terms and try to simplify them so that there are no pairs of brackets left. But in this problem, the goal is to factorize. The goal is different. The goal is to write this expression, if possible, as a product of factors. Okay? And then you can immediately see that if I ask you how many factors are involved in this expression, you would tell me 2 factors of x and 1 big factor, x squared plus x plus 1. And if I go here, I have 2 factors again, x and x squared plus x plus 1 as a whole. And when I go here, I have 2 factors, 3 and x squared plus x plus 1. So you see that in these 3 expressions, there is only 1 factor in common, and that is x squared plus x plus 1 as a whole. Yes, so the only thing that I can pull out is just x squared plus x plus 1, and then what is left here is just x squared, and then I have negative sign. What is left here is x, and what is left there is positive 3. Be careful. This is the end of the story. Yes, you are not allowed to multiply things back. The goal is not expanding. And if you don't mind, let me solve one problem and then go to the next method that I want to describe. Okay, so I can start from here. So number 6, 4a, 3x minus y to the 2, and then I have plus 6ax minus 3x plus y, and then I have plus 10ay, and finally 3x minus y. Okay? Okay, so if I want to start factorizing this, I need to realize which factors are in common. Okay, so between numbers, it is easy. Yes, you see that between 4, 6, and 10, 2 is in a common factor. And I have a here, and a here. So I can consider that one as well. And then I see that I have a factor of 3x minus y 2 times here, 1 times there, but not exactly 1 here. But then you can immediately realize the difference between the factor 3x minus y and minus 3x plus y is just a matter of its extra sign. Okay, so whenever this is needed, remember that a minus b is actually equal to minus b plus a. So you see the negative sign, positive, positive. But a minus b, of course, is not equal to b minus a. This is wrong. But a minus b is equal to negative b minus a. If I multiply this negative sign inside, it becomes negative a, negative b, positive a. So be careful. And then you see that here I have more or less the same expression with the wrong sign. Yes. So whenever this happens in algebra, the trick of pulling out a negative sign will usually work. So before I start doing something here, I would write this is equal to 4a, 3x minus y to the 2. I pull out a negative sign out. So then this becomes negative 6ax. This becomes positive 3x, but then this becomes negative. So it's very good, yes, because 3x minus y is the common factor now. And this, by the way, is important. If you don't realize it, that is wrong, because we want to factor, we want to pull out as much as possible. So if you cannot realize that this is indeed the case, then you only factor a number 2 and a out. And then I would say that this factorization is incomplete. Yes. So now everything is ready, so I can factor the common factors out. What are the common factors here? Between the numbers, as I already said, I have a factor of 2. And then I have a factor of a here, here, and there. So I pull it out. And then I have a factor of 3x minus y common in all these expressions. I can also pull that one out. So let me put equality. So 3x minus 1. But then I open a little bit bigger bracket here. And then what is left from here? I pulled 2 out, so 1, 2 is left. I pulled a out, so nothing is left here. And then 3x minus y, one of them is left. Because I only pulled one of them out, there were 2 factors of 3x minus y here. Let us go here. I have a negative sign. I pulled 2 out, so 3 is left if I divide. And then I pulled a out, x is left. And I put 3x minus y out, so that's the only one left. And finally, the last one, I pulled 2 out, so 10 divided by 2, 5 is left. I pulled a out, y is left. 3x minus y is also pulled out. Of course, this is already, I agree, in the factorized form. The factors are 2, a, 3x minus 1, and the whole expression. But nobody leaves this in algebra usually like that. We can simplify this more. And then you will see that in this case, it is actually indeed necessary to simplify. Let us see why. This becomes 2a, 3x minus y. If I multiply this inside, it becomes 6x minus 2y. And then 6x minus 3x is 3x. And minus 2y plus 5y is what? Positive 3y. You see, it's crucial to simplify. Because if you stop here, this is still not complete. Why? Because coincidentally, the simplification gives me an expression that can be factorized in its own turn. Yes, I can factor a 3 out. So this can be 3, and if you don't write it, I would consider it as an incomplete factorization. And then this 3 will be multiplied by that 2. It will give me 6. It becomes 6, and then I have a 3x minus y, and then I have x plus y. So this is the full form factorization of this expression. Okay. So one remark that I want to mention before going to the next step is this. We will learn a lot of methods of factorizing polynomials. But then I want to mention that this method of pulling an expression, a common factor out, if possible, from all the terms, has the priority on the other methods. So what I want to write is that method 1 has a priority method 1 has priority over all coming methods. Of course, if possible. So I will explain about this remark, but let us just remember that. I hope that I have spelled priority, Priority, correctly. Yes. Okay. The second method is the using identities. The identities we learned will help us to factorize some polynomials. Yes. So let me clean this one. I can also clean this part. Yeah, of course, this is expectable, yes. For example, so let me write method 2. Using identities. Yes, I can use identities to factorize. This is expectable. For example, if you have a minus b times a plus b, then you get a squared minus b squared. Yes, when we were learning about identities, usually this side is given to you and you're supposed to write it by expansion like that. But then the goal is factorizing now. So it means that a squared minus b squared, if given to me, if I remember this pattern, I can write it in this form. And this form is in a factorized form because this has been written as a product. So this is, I want to tell you that this is expectable, that if I can use identities to factorize polynomials. It's a little bit harder because you need to realize, you need to recognize the pattern. The right-hand side of the identity is given to you. You need to realize the pattern and then to go backward to the original form. This gives you the factorization, yes? So you need to practice to train your eyes to detect these patterns, okay? So let us separate this. For example, I can talk about a quadratic identity. Okay, quadratic identity. So let me write it the other way around. So it means that whenever you see this combination, you can write the original form, a plus or minus b to the 2. When I was talking about identities, I usually write this one and on the left and put this one on the right. But in factorization, that is exactly the same idea, but written in a reversed order. Okay, so let me give you some examples. So you need to train your eyes to see this pattern quickly. So I would mention again factorize. Yes. So let us write one. It's x squared plus 4x plus 4. Yes. Okay. So the chances that I can factorize this using the quadratic identity is good. Yes. First of all, I have 3 terms. 2 of them are complete squares. You see, this identity contains 2 complete squares, a squared and b squared. But you need to do some scratch paper checking yourself. So you need to be careful that this really is a quadratic pattern, yes or no. How we should do that? I see that I have 3 terms. 2 of them are complete squares. So it means that I'm a little bit dubious that it might happen that this is a quadratic pattern. So what should I do? I need to take the square of this one, it becomes x. I take the square of that one, it becomes 2. And I multiply them, and I multiply by another extra 2 myself because of these 2 in the formula. So then you see 2x times 2 is 4x, and exactly 4x is what is sitting here. So it means that, yes, this is exactly the quadratic pattern. So when you realize that, then it is easy to answer it. So you put the power of 2, you put the square of this one here, the square of that one here, and if this sign is positive, you put positive in between. Oh, sorry, the square of 4 is 2. Yes, and then if this is positive, you put positive. If it was negative, you put negative. Yes, so that's the factorization. By the way, why this is a factorization? Because x plus 2 to the 2 can be written as x plus 2 times x plus 2. So x plus 2 to the 2 is actually a product. Okay, number 2. 4x squared minus 4x plus 1. Okay, again, let me repeat these things once more. I have a trinomial, 3 terms. 2 of them are complete squares. Is it indeed a quadratic pattern? Let us check. You go to a scratch paper, you take the square root of the first complete square, it becomes 2x. You take the square of the second one, multiply it here, and you always multiply by an extra 2 because of this factor of 2. Then what happens is 4x, and 4x is exactly what is sitting here in the middle. So that's exactly the quadratic pattern. So what you do, you open brackets, you put a power 2 here, the square of this one is 2x, the square of this one is 1, but this time, because the sign is negative, you put negative here. Yes? Okay, let me go to the next one. So number 3, I have 9a to the 4 minus 12a squared, and then I have plus 4. Yes? Again, let me repeat it once more. I have a trinomial. 2 of them are complete squares. So I am doubtful that it might happen that this is a quadratic pattern. How can I convince myself if it is or it is not? I go to a scratch paper. I take the square root of this one. It becomes 3a squared. I take the square root of that one, it becomes 2, and then I multiply by an extra 2 myself. So 2 times 2 is 4 times 3 is 12a squared, and 12a squared is exactly what is sitting in the middle. So this is indeed a quadratic pattern. So then I put 3a to the 2 here. and 2 here. Because this sign is negative, I put a negative sign there. Okay, so that is the factorization of this expression. Okay, let me mention one more here. So number 4. So what happens if I have minus 4a squared minus 9b squared positive 12ab, I think, yes. Yes. Again, you might see that I have a trinomial. Trinomial means a polynomial with exactly 3 terms. And 2 of them seems to be complete squares, but not exactly, because of these negative signs, okay? So if I want to keep it in that form, I cannot continue because I need to have them positive. Okay, I told you, whenever you have the wrong sign, you need to take the negative sign out. It might work. So I will take negative sign out first. This becomes 4a squared. This becomes positive 9b squared. But then this becomes negative 12ab. Okay, at least now they are with this correct sign. Yes. But is this a quadratic pattern? You see, I have a trinomial. 2 of them are complete squares. I go to scratch paper. Take the square of this one is 2a. Multiply. Take the square of this one is 3b. And then you multiply an extra 2 there. It becomes 12ab, which is the third term. That's exactly. But you don't need, you have to remember to put this extra negative sign. So it becomes negative. And then I would write this to power 2, take the square root of this one is 2a, take the square root of that one is 3b, and then put a negative sign in between. So that would be a factorization of your polynomial. Okay, now do you remember I told you something about that priority remark? Okay, so let me give you now this example, number 5. So I have 9x to the 3 minus 48xy, x squared y, and then I have plus 64 y squared x. Okay, so the only thing that this has is that that's a trinomial, but it seems that I don't have any complete squares. But look, I told you that whenever you can pull out some factor from all the terms, what we learned before, that has the priority over the coming methods. Yes. So here you can see that can I factor a number out? Not apparently, but can I factor an x out? Yes, I can factor x out. So before start thinking about what should I do, you do this step and then think, can I continue? Is it enough or I can continue even further? So what I'm trying to say, as soon as you see that you can pull something out from all, I emphasize, from all the terms, you do that. So here I factor x out. What is left here is 9x squared. What is left here is 48xy. And then what is left there is 64y squared. Yes, this is already in factorized form, by the way. This is there are 2 factors. One of them is x. The other one is the whole expression. But when we say factorize, it means as much as possible. This phrase is implicit in the word factorization. Okay, now this has 3 terms, so it's a trinomial. This has 2 complete squares, so I get suspicious that it might happen that this is a quadratic pattern. If you don't believe it, you go to scratch paper, take the square root of that. Okay, sorry, I had to, the charge of my AirPod was finished, so I have to replace it. Okay, so I was telling you that, so if I ask you how many factors are there, one factor is x and the other factor is that one, but this has, it's a trinomial with 2 complete squares, so it might happen that this is actually a quadratic pattern. So I took the square root of that one, and then I multiplied an extra 2 there, yes? And if I calculate this, 2 times 3 times 8 is exactly 48. And then I have xy. So this is exactly 48xy. And this is what is sitting in the middle. So I continue like that. X is I have to write x, and then I have put the power of 2. A square of that one is 3x. Square root of that one is 8y, and the sign is negative, so I put a negative sign here. So that's a factorization of that one. Okay. The next one, we can write it in this form. 6, we have 4a plus b to the 2, and then I have minus 12ab, a plus b, and then I have positive 9. Okay, is this a quadratic pattern? Of course, in principle, this is not a trinomial, because if I expand them, they have more terms, but it is written in the form of a trinomial, yes? And then I have again 2 complete squares. So if I go to scratch paper, if I take the square root of this complete square, it becomes 2a plus b, yes? If I take the square root of 9, it becomes 3. And if I multiply an extra 2 myself, as I always do, it becomes 2 times 2 times 3 is 12, and I have a plus b. That's exactly what you see in the middle. So what should I write? I should write this to the 2. I take the square root of that, which becomes 2a plus b, and then I have the square root of that is 3, but the sign is negative. But usually, we don't leave this like that because these brackets can be removed, yes, by multiplying this in. So then it becomes 2a plus 2b minus 3 to the 2. So this is a factorization of that expression. Okay. Let me write one more here. 7. We have x plus 2 to the 2 plus 2x plus 2, and then I have x minus 2y, and then I have plus x minus 2y to the 2. Yes? Again, you see that even though this is not a trinomial, but it is written in the form of a trinomial with one term, the second term, and the third term. And the good point is that I have 2 complete squares. Yes, so it might happen that this is actually indeed a quadratic rule. And indeed it is, yes. If I take the square root of this, it becomes that. Square root of that, it becomes this. And if I multiply an extra 2, it becomes this. So everything is in order. So this is actually can be written in this form. X plus 2, and then x minus 2y. But this one is positive, so I have to put it here. Yes? But then I have to continue. So x plus 2, it doesn't need any brackets. This doesn't need any brackets here because that's also the same thing. But then what happens? X plus x becomes 2x, and I have minus 2y, and then I have 2 to the power of 2. Yes? But of course, that's completely okay. But if you stop there, it's not complete yet. Because coincidentally, I get an extra and a common factor again too. So I have to pull it out if I want to have my factorization to be complete. Yes. So what I do, I again factor a 2 out. It becomes x minus 1 plus x minus y plus 1 to the 2. And then because that's a product, if I want to raise it to power 2, the first one to the power of 2 becomes 4. And then I have x minus 1 plus x minus y plus 1 to the 2. Yes? So that is the full factorization of that expression. Okay, so I think that these examples are enough for working with quadratic identity. So let me change my identity to conjugate identity here and give you some examples. So still we are in using identities. Yes, but this time I switch to conjugate identity. Yes. Okay. So the conjugate identity, as you might know, is A plus b, a minus b, is equal to a squared minus a squared, but I told you that in identities, we go from this direction to that direction, but in factorizing, I go from this direction to that direction because my goal is to write this expression as a product of polynomials, or as a product. Okay, so let me give you again examples. The best thing to do is just solving examples. So example, factorize. So let me start with a simple example. So yeah, so I have, this is very simple, of course, x squared minus y squared. So it's clear that's a conjugate pattern. So it becomes x minus y times x plus y. And it doesn't matter if you write x plus y times x minus y. They are the same. It was so easy. So number two, let me write another one. X to the 4 minus y to the 4. Yes. So I can see that this can be written as x to the 2 to the 2 minus y to the 2 to the 2. Of course, you don't need to write these intermediate steps. I'm just doing it once so that if you have some problems, you can just learn them. So then this becomes x to the 2 minus y to the 2 times x to the 2 plus y to the 2. Of course, this is already in product form. This is the one factor. This is another factor. But I told you when we say factorize, it means that as much as possible. So I can just use, again, another pattern of conjugate appears here. So I can write x minus y times x plus y, and then x squared plus y squared. And if I want to be in the set of integers, I cannot factorize this expression. I need to use complex numbers if I want to insist to factorize this expression. So this is why I stop here. Okay, another example. So another example that I can mention is this one. Again, I want to emphasize on that priority remark. Do you remember? So I want to factorize this expression. Again, you see, instead of thinking what to do, what you can do is just to see that there are two factors in common, x and y. Without thinking, try to take this out and see if that your factorization is indeed complete. If it is complete, you are done. If not, what is left is much simpler than the previous one. Okay, so what I do, I factor xy out. And what is left from here is x squared. And what is left from here is y squared. Of course, this is in factorized form with three factors, x, y, and x squared minus y squared as a whole factor. But then I can continue because immediately you realize that you have a conjugate pattern. So you can factorize it more and write this. So xy times x minus y times x plus y. Let me give you another example here, number 4. So what can I do with x to the 4 minus 16? Yes, that's also simple, yes. So you can write it as x squared minus 4, x squared plus 4, yes. That's a conjugate pattern. But then x squared minus 4 can be factorized more, but not this one. If I want to factorize this, I need to work with complex numbers. So I do not factorize that, and I only factorize this. This becomes x minus 2, x plus 2, and then I have x to the 2 plus 4. Yes. So what can I do, for example, here? 81 x to the 4 minus 16 y to the 4. Yes. Can I pull out something? The answer is no. So I have to recognize the pattern. So the pattern is completely clear. It's a conjugate pattern, yes. So I can write this as 9x squared minus 4y squared multiplied by 9x squared plus 4y squared, yes. The reason is that 81x to the 4 is 9x squared to the 2, and 16y to the 4 is 4y squared to the 2. But then you realize that this is, again, another conjugate pattern, so I can write 3x minus 2y times 3x plus 2y, and then I have 9x squared plus 4y squared. Yes. Let me give you some more examples here. So what happens if I have this situation, for example, x squared plus x plus 1, and then I have to the 2, I have x squared minus x plus 1 to the 2. Yes, my goal is to factorize this. And I hope that you can immediately recognize the conjugate pattern. If you take this the box and this one the circle, what you see is box to the 2 minus the circle to the 2. And whenever you have this, it's a conjugate pattern. So what can I do? I can write the box, which is x squared plus x plus 1, minus the circle, x squared minus x plus 1. And then another time, the same two expressions added together. So x squared plus x plus 1 plus x squared minus x plus 1. Okay? So factorization is more or less finished here, but simplification is not. We have to simplify as much as possible. So I multiply this negative sign inside, so this becomes x squared plus x plus 1 minus x squared plus x minus 1. And here I can just remove the brackets because the sign behind them are both positive. Okay, and then here x squared and negative x squared are canceled, 1 and 1 are canceled, x plus x is just 2x. So it's 2x. And here x and x are gone. X squared plus x squared is 2x squared, and then 1 plus 1 is 2. Even though we have done a lot to simplify this, but it is not finished because the goal is factorization, and then coincidentally, you see that a common factor actually pops out. So I have to take that 2 out away again. So this 2 will come out, and this will multiply here, so it becomes 4x, x squared plus 1. So that is the factorization of this expression. Let me give you 2 more examples here. So I have 7. I can write it as 1 minus 2x minus 3 to the 2. Okay, so if I want to factorize this, so you can realize that this 1 is actually a complete square, so that is the difference of 2 complete squares, and whenever I have the difference of 2 complete squares, I have the conjugate pattern. Okay, so what can I do? I can write it as 1 minus 2x minus 3, and then another time I add these two expressions. Yes, but then I multiply this negative sign inside, it becomes negative 2x positive 3, and I can just safely remove that bracket because the sign behind that is positive. And then what happens here, 1 and 3 becomes 4, and then I have minus 2x, and here 2x, and 1 and minus 3 becomes minus 2. But be careful. Then I have a common factor now again. It was a coincidence here. And I have another common factor of 2 here. So I pull 2 here and here. So I will get a 4 at the end. So a 2 coming from here and a 2 coming from here will multiply each other, and I will get 4. And then I have 1. I have 2 minus x here. And then I have x minus 1 here. And this is the factorization of that expression. Okay? And then if I want to write one more, and then we go to the last identity for this session. Okay, so another example, so let me call it 8. So a plus b to the 4 minus a minus b to the 4. Yes. So if I want to factorize this, again, I have the difference of complete squares. So this means that I can use the conjugate identity. So this becomes a plus b to the 2 minus a minus b to the 2. And then I can write a plus b to the 2 plus a minus b to the 2. Yes. But then this is again another conjugate pattern. So then what can I do? I can write a plus b minus a minus b multiplied by a plus b plus a minus b. And then here, of course, this is not a conjugate pattern. So let me just keep it like this for the time being. Yes. Okay, but let me simplify this expression. So I open these brackets, so it's a plus b, but here minus a plus b. Here, both of them are positive, so I safely remove them without any changes. But here, I cannot continue, but it is not good to keep it in that way, so I have to simplify that. So simplification here needs a quadratic pattern. So don't get confused. Sometimes I have to use factorizations and identities together, yes? Because if I don't do that, first of all, I cannot factorize this because this is the sum of complete squares. For factorizing the sum of complete squares, you usually need to go to complex numbers, okay? And then, of course, it's better not to leave it like that if I can simplify. So whenever you can simplify a factor, you have to do that, yes? Even if you are using the quadratic patterns, any sort of identities, any expansions, yes? So what I'm trying to say, I have to do this here. Otherwise, I have to keep it in this form. But nobody keeps this one in this form if we can simplify it more. So this becomes 2ab. So what I'm trying to say is that might be you think that this is not according to the logic as I told you. But now remember, factorization is done here. I have written it as a product. But the reason that I am using identities to expand is because I want to simplify that one single factor. Yes. So then it becomes a squared minus 2ab plus b squared. Okay, here a and a are gone, so it's 2b. A and a is 2a. B and b are gone. And here a squared and a squared is 2a squared. 2ab and minus 2ab are gone. And b squared and b squared is 2b squared. And then you see that again it's a coincidence. So this 2 is a common factor. I can pull it out. So a 2 coming from here multiplied to each other is 8. So I will get 8ab, and then I have a squared plus b squared. And I cannot factorize this more than that. Okay. Now, the last thing that I want to talk here is this identity. If you go back to lecture number 4 of identities, you will see that I talked about this identity there. I think it was lecture 3, not 4. I'm not sure, quite sure. So let me write the identities here for you. So the identities, if you remember, were this. What happens if I have the sum of cubes or the difference of cubes? Yes. Conjugate identity is only useful when I have the difference of second powers, squares, this difference of squares. But what happens if I have the difference of cubes? In the conjugate pattern, usually if I have the sum of squares, I need the complex numbers to go further. But here, if I have the sum of cubes, still I can do that. Yes, so if you remember from that lecture, this is the factorization. Yes, and this one is this. Yes, when I was talking about identities, I wrote this one on the left-hand side and this one on the right-hand side. But now the point is to factorize, to write this expression as a product. So this is given to you. You should be able to write this one yourself. Okay, and let me give you one example with 3 examples, actually 3 items, and then we are finished. So factorize. So number 1, I have 8x to the power of 3 plus 27y cubed. Okay, so you see that this is the sum of 2 complete cubes. So in principle, I can write it as 2x to the 3 plus 3y to the 3. Yes. And then this will play the role of this a here, and this will play the role of that b there. So I can use this formula to factorize this expression. So this becomes 2x plus 3y, a plus b. And then I have a squared, which becomes 4x squared. And the product of them with the opposite sign, so 6xy minus 6xy, you see a and b with the opposite sign. And then this one to the power of 2. Of course, there might be some possibility that this one can also be factorized, but for the time being, don't worry about that part, okay? We will come to that. Okay, number 2. So number 2, I have 64 x to the 3, y to the 6 minus 8 x to the 6, y to the 3. Okay, it seems that this is neither this pattern nor the conjugate pattern. The reason is that I told you, whenever you can factor a common factor from all the terms, this has the priority. So you see that 8 is a factor in common, x to the 3 is also in common, y to the 3 is also in common. So first I need to factor 8, x to the 3, y to the 3. This has the priority. And then what is left from this is 8, and then I have y to the 3. And what is left here is just negative, and then I have x to the 3. Yes, but then it reveals that this pattern emerges, this pattern of the difference of cubes. Yes, so I can use this identity now. So this becomes 8 x to the 3, y to the 3. This becomes 2y minus x, the cubic root of this one minus the cubic root of that one, if I have the difference of cubes. And then the bigger one should be written in accordance to this one. So the first one to the 2, the second one to the 2, the product of them with the opposite sign. So this becomes the first one to the 2, the second one to the 2, the product of them with the opposite sign. That is the factorization of that expression. And finally, let me do this one. X to the 3 minus x minus 1 to the 3. Yes. So this is the difference of cubes. So I can write it as the cubic root of that minus the cubic root of this. And then I need to write the second brackets in accordance to the first bracket. This one to the 2, this one to the 2, and then the product of these two with the opposite sign. So it becomes positive. Okay, and then you have to simplify. In simplification, of course, it's inevitable. You have to expand and use identities. So then I would write x, I would write minus x plus y. I apply this negative sign in. X squared is just x squared. I multiply x squared minus xy. And then this is the quadratic pattern. X squared minus 2xy plus y squared. But then this x and that x are gone. So what is left for me is y. And here x squared, and x squared is 3x squared. And minus xy minus 2xy is minus 3xy. And finally, I have y squared. So that is the factorization of this polynomial. Okay, thank you. So I hope that you have enjoyed the video, and then I will upload also a set of problems that you can solve using the material that I covered here, and I will give you the link in the below the video in the description actually part. Okay, uh, till next time that I upload another video, goodbye. Thank you.